Okay, so in this video, we will discuss table read-write instructions. Okay, what do I mean by table read-write instructions? Here are the instructions, and really the purpose of these instructions are to move data from program memory to data memory. What do I mean? Well, program memory, as you might remember, is arranged into 16-bit words, and we arrange them as each word is split into two bytes, and they're arranged accordingly. And we have these address, and technically we need 21 bit to address all of them, but we don't use all 21 bits for the PIC18F4321 we're using. We just use a few of them, which are 13 bits, and that's what we've seen, what we have been dealing with. Okay, so sometimes you have the situation where you have this particular data and it's actually in program memory. And program memory, if you guys remember, it's flash, so it is non-volatile, so it stores them. Okay, so they are stored in memory, and the reason why is because maybe we have some sort of a conversion table. I'll give you an example towards the end of these, but I just want to, at this point, I just want you to know why do we use them and how do we use them, and then I'll give you an application. But for now, I have program memory, and this program memory is hard-coded by the programmer, so we need that data because we're gonna keep using it. It's not code, it's actually data, actual numbers, maybe a conversion or something. Okay, and let's assume that these are the numbers, and these are the numbers that we'll actually use. So these are the numbers that are stored in program memory. So every single time I want to use I want to use this data. What I need to do in order for me to compute anything in my program, I need to move them to my data memory, because data memory is where I do everything I do, where I pull some, because my instruction go to data memory. It doesn't deal with program memory. If you guys remember, all my instructions, they jump in program memory, but anytime I want to write or read or do anything, it actually goes to data memory or the working register or one of the special function registers, which are part of data memory. But I never actually wrote into program memory or read from program memory. And frankly speaking, writing into program memory means that you are actually writing your program into the microcontroller. So it's actually writing the flash. This is something we're not going to be doing unless you're developing the programmer itself, which you probably have bought by now, which is the Picket 4 or Picket 3 or Picket Snap, whichever Picket you actually use. It's something you connect to the microcontroller so that you can, whatever code we write, you can actually upload it to the microcontroller. Somebody has to program it. So these instructions are usually helpful, and they're called the table write. We're not going to be doing this because we're not developing a programmer, we're just using it. So what we're going to be focusing on are just the table read instructions, and these table read instructions will make this movement of data between program memory to data memory much easier. Remember, we have two different addresses, and this is 16-bit, this is 8-bit, so it's kind of like tedious to do. So what I want to do is I want to focus on this table read, and this asterisk is part of the instruction, so you're going to have to write it. And the plus, minus, and plus, then it's actually similar to the post increment, pre increment, the one we said with the FSR. So we're gonna focus on the table RD first, which is table read first, and then we're gonna go forward. So I'm gonna explain it on the slides, and then we're gonna go and implement it in MPLAB shortly. So okay, so how do we read? Well, this instruction actually goes to the table, to the program memory, and reads some sort of an instruction. But in order for you to tell it what to read, you need to actually tell it, well, you need to read which memory row do you want to read. Is this memory row? Is this memory row? Or what memory row? And we're talking about row in here. I'm going to deal with program memory as if it actually has bytes. I'm not writing instructions. I'm writing data. So might as well just write them into byte at a time. Yes, these will be rearranged so that they're right next to each other as one row of 16-bit. But for now, we're going to just deal with program memory as, okay, it has 1 byte in here, 1 byte in here, 1 byte in here. I can write each byte separately, and they don't have to be aligned. They don't have the least significant bit of the address. It doesn't have to be 0 and whatnot. Bottom line is, I'm writing into program memory, I'm writing bytes, okay? So, and these are the bytes I have. In order for me to figure out what byte to write, I need to tell the assembler, well, you need to write this particular one. And it turns out to be that I need some sort of a pointer, kind of like the FSR0 that we use. And that pointer is called TBL, which is table pointer. So I'm going to have some sort of a special function register called table pointer. That table pointer will contain an address in program memory. So the size of this table pointer should be exactly the same as the address for program memory, which is the same as program counter. And if you go to the data sheet, you're going to see you can actually scroll all the way up, and you can see that you can look for TBL pointer, and you can see, let's do that. Okay, TBL DRP, well, table PTR, and you can see that you're gonna find it. Well, you're gonna find a bunch of them. Like, look for it. Let me pause and look for it. Okay, so I found it under the special function registers, and it is on page, what page is this? It's page 62. Okay, so you're gonna see that this table pointer, well, it's not necessarily table pointer only. You're gonna have we have U, H, and L. Well, why is that? Well, we have 21 bits. I can't fit it in 1 byte. Remember, it's like these are special function register. They're part of data memory. So I'm gonna have to split these 21 bits. Frankly speaking, we're only use 13 bits for the PIC 184321. We're not gonna use all 21 bits. But anyway, you get the idea. We only need we need 3 locations. Okay, so let's see these 3 new locations. So this table pointer is gonna be split into table pointer low, and it stores bits 0 to 7. Table pointer high will save bit address basically from 8 to 15, and then the upper table pointer upper. Okay, it stores from 16 to 20. And if you think about it, these are 5 bits, so there are 3 more bits here, but we're not going to be using them because we don't need them. Okay, so what does that mean? Well, it means that we will take that address and we're going to put it in that table pointer. So in order for us to read that particular memory location, before we actually read it, we're going to actually go to the table pointer and put that address in it, and we're going to have to read it. So I'm putting that address means, okay, we're going to take that 2 and 0. This is 1 byte, and we're going to put it here. We're going to put that 1 and 0. We're going to put it in here. And for the for the PIC 18F4321 that we're using, we don't have the upper. Okay, we just don't, because we only need 13 bits. So not even those 15 bits. We're just going to be using those here, and a few, like, we're going to leave a few bits in there. Okay, so technically we need to put these into these 2 special function registers. And once we do, we're gonna, okay, so the first thing you do is you put that table pointer, you pointed, now it's pointing to that particular location in program memory. Now you issue TBLRD, and if you can see it, this is the data sheet. It doesn't tell me it takes any argument or any operands. Well, it turns out to be because what it does, it reads that particular memory location, that number 11001001, and it put it in something called table latch. Okay, so it's going to take, so every single time you issue this command, what it will do is it will go to the table pointer. It says, where are you pointing to in program memory? Oh, this location. Okay, I'm going to take that particular location, I'm going to put it in another special function register. It's called tab lat or table latch. Okay, so it will have that. Now I can do whatever I want with this. This is just a special function register. I can move it to the workman register. I can move it to a certain place in memory using move FF, whatever you want to do. Now I want to talk a little bit about the, so this one here, I just moved it to that particular location. Okay. Now I want to talk a little bit about the other instructions, the one we have in here. You can see that after we did the TBLRD, what happened with the pointer is nothing. It's still pointing to the same exact location. So we issued a command to read, and we kept the pointer wherever it is. But generally speaking, when we're moving data from program memory to data memory, they're arranged in rows of bunch of data. If I'm only interested in 1 byte, might as well just hard code it as move LW or some sort of a literal. But if usually you have like a bunch of rows and rows and rows, let's say 100 rows or so. So what you need to do is you need to move that pointer forward, kind of like what we did with the FSR0. These are exactly the same. So if you put a plus after that asterisk, it will actually post increment it. So if you issue this command, what it will do is it'll, okay, here's where my table pointer is. I'm going to read it, put it in tablet, and now I'm going to move the pointer forward 1 location. Now I'm pointing to the next location. I didn't read it yet, but I'm pointing to it. Okay, so if you issue another one, what it will do is actually would read that particular value, put it in tablet, and so forth, and you can actually do this. And you can see that today we're going to actually utilize this functionality to read a table, a big table. It's not a big table, it has like 10 entries, but you get the idea. The negative actually moves backwards. Instead of moving the pointer forward, it moves backward. This one here actually moves the table before it reads. So this is a pre-increment. Exactly the same as what we saw in the FSR, at least in terms of function, and not in terms of functionality, but in terms of the way you deal with this. So what I want to do right now is, before I actually do the applications, I just want to show you how we actually do this. How do we write into program memory, and now how do we move it, and what's happening in there. So let's go to MP Lab. Okay, so we're going to do that here. We're going to move that older program, and we're going to say that we are here. We are in writing code. Okay, so now it becomes important, the psect code and whatnot. Let's me put an op in here before I forget. Okay, and I'm going to do stop branch stop. Okay, So, all right, so now we have that. Now, in order for me to write data, well, I need to write it in somewhere in program memory, so I'm gonna have to tell it here. Now, if I put it under code in here, I can write the data in here, but this is data, this is not code. Okay, and it's actually important to tell the assembler that you're writing data. Well, it turns out to be, this is why this particular assembler, actually it's different than the older assembler. In the older assembler, you had to specifically tell it to go to location 200 or location 80 or location, every location here in memory has a special functionality. But in this particular assembler, all these definitions are included in that xc.inc. All you have to do is just tell it, well, I have a new program sector, and this new program sector actually have data in it. So whatever you write under this psect or this program sector is actually just data. This does not have to be aligned as 16-bit words or anything. It's not instructions. You can write them 1 byte at a time. Okay, so I'm going to show you how to write this. So now we have a psect data. You can still use, some of you ask me, what about the org 0 to 100? Like, do I have to use it or not, whatnot? Like, because some of the labs ask you to specifically write in a special location. The specifically writing in a special location, this assembler directive is actually telling it, hey, go to location 200. This new assembler, this is not an absolute number. This 200 is relevant to wherever program sector data actually start. This is 200 from the start of the program data. You can look to see where this data is. Generally speaking, you're going to see it, if I remember correctly, right after my code. We're going to see it in a few minutes where it will write it. But I think it will write it after my code. It doesn't have to be sequential. The data is not necessarily going to be written before the code. Okay, I'm telling it, this is code. You can put it before the code, after the code, it doesn't matter. The assembler will know where to put it. Okay, generally speaking, nowadays, you do not use the org. This is old, and if you actually look at the data sheets, you're going to see that they tell you, generally speaking, you're not going to have to specify exactly what location in memory you need to write into. Okay, and the reason why is because if you move to a different pick, different family or something, these definitions are already included in the XC, and it will know exactly where the data should be. You don't have to figure out that it's location 200 or whatnot. Okay, so we're going to write these data. So now how do we write the data? Well, we are in program memory. It's as simple as saying, well, we're going to define a byte, okay? And that byte is going to be 11001001. This is actually that byte in here. If I'm not mistaken, let me just see, where is it? I can't see it. Okay, it's that one here, 11001001. Okay. Anyway, it doesn't matter. It's just a byte. So what this does, it exactly is. So DB is actually not an instruction. It's actually an assembler directive. This is something I'm telling, hey assembler, the one that is going to read my code in here and interpret what this start mean and what this stop mean, and put them, oh well, I have a typo in here, and put what that stop has to be or what address it is. I am telling you, now you have a byte, please place it in that data, and it will actually go here and place it. So I'm going to put a bunch of these data. It's actually, I'm going to put 0011001B, 0001001. B stands for binary, 11010010 binary. Okay, so what this does, you're going to see it. Let me show you what's actually happening. It actually went in and went through all the way through, and you can see that I'm going to pause it. I can reset it, and it will take me directly to the reset vector, which is 000, the program counter. And then I'm going to step into here, and it took me in. Look, it took me to here. This is where my NOP is, and this is where my stop. So basically, this is where my code is. So the assembler, for some reason, I mean, a few minutes ago, I actually put it after my code, but the assembler decided to put that code has to be before. Okay, so it put my code in here. So let's see, what do I mean by put my code in here? You can completely ignore that. This is here, it's trying to interpret these instructions. Whatever I put in here, it's trying to interpret them as machine code. Remember the machine code where we interpret all these knobs and bra into ones and zeros? So if you put these particular in these particular location, this is actually what it means. This is meaningless. We know that it's data. We know it's not part of our program. So we're not, the assembler is not gonna implement this. It's not gonna send it to the CPU to implement it. It is just storing them. So, and if you think about it, this here is C9 is the lowest byte. This is my C9. The next byte is actually 35 in hex. This is my 35 in hex. The next byte in here, which is actually in a new row now, it's going to be 11, and this is basically my 11. And this one here, which is D2, it's here. Frank speaking, I could have wrote it in a little bit different way, which is basically define word. Okay, instead of byte, we can define it as a word, and I could have just done it this way: 35C9 and also 0x D211, and these two are equivalent. So look, I'm gonna rerun this. These two are equivalent. The word, if you guys remember, the word is actually 2 bytes. So this is the lower byte, this is the higher byte, this is the lower byte, this is the higher byte, and you can see it did exactly the same thing. So you can keep it either way. Okay, so that's good. So now we know how to write into program memory. This is not moving anything. I just basically stored it. Now every single time we turn on that microcontroller, you're gonna see that this data is available to you to do whatever you want. Now what I want to do is I want to move it to my data memory so that I can do some useful things with it, because these numbers might mean something useful to me. Okay, so the way we're going to do it is, again, we're going to have to deal with the table pointer. I want to basically tell, in order for me to use that table read, I need to tell it, hey, point to this particular location. This is a data. I want you to do it. So what I'm going to do is I can definitely figure out where it stored it, but I don't want to. So I'm going to tell it that this is actually, let's do this. I'm going to give it a label, and I'm going to give it, because it's going to be a lookup table. Later on, you're going to see that we're going to put a lookup table in here. Okay, so I gave it a label, and now what I need to do is I need to go that lookup here. This is an address. This is address in program memory. That means it is one of these 13-bit, 21-bit, but we use only 13-bit in here. So it's one of these. So I need to put it in the table pointer. Okay, let me just do this here. I will do that here, and I'll do this in here. So I just want to remind you, we're doing that table pointer in here, but of course the table pointer is split into 3 places: the lower, the high, the upper. Okay, so we need to actually write them separately. So let's do that. So okay, so how do I do that? Well, inside my my code. Now this is code because I'm writing into some sort of special function register. So inside that code, what I'm going to do is I will have to tell it, okay, well, we need you to write that lookup table into that table pointer. So let's start with the low. So what I'm going to do is I'm going to say move LW, the literal, into the working register. What am I going to move? Well, I'm going to move lookup, but lookup is more than 8 bits. Okay, so it's not going to fit within my working register. Turns out to be that there's actually an operator within this assembler. Okay, and that operator tells me low. Okay, and that low, all it does, it will take the lowest 8 bits. That is in lookup. So it'll take the address, whatever the address is, it will take the lowest 8 bits and we'll just move it in here. So that low will just basically, it's kind of like, you can think about it as a masking. I'm just putting FF towards the end, like kind of like I'm doing, well, 0 0 and then another 0 0 and then FF, and then I'm ending it with the lookup here, with the location here. But I don't have to deal with this. Okay, so there's an instruction for me. So now the lowest 8 bits are already in my working register. All I have to do is just go and write it in my table pointer L. Okay, so I'm gonna do move WF table pointer L. Okay, this assembler likes, if it's a special function register, it likes to be written in capital. It will, I think if you wrote it in small caps, it's not going to recognize it. Okay, all right, F and A, I could be mistaken, but this is what I remember. All right, so we're going to do this. Now my table pointer has that, like similar to that 0 3 in here. Okay, now I need to move in the next 8 bits. Okay. All right, so how do we move them? They're not actually 8 bits because what we have is 13 bits. So I don't have 16. But anyway, we're going to move that. And we're going to do move LW. Very similar, but instead of the low, now I'm moving the high from the lookup, okay? And I'm going to move them from the working register to table pointer high, F and A. Now I can stop right here because we're dealing with a 4, 3, 2, 1. Everything else is a bunch of zeros, but I just want to show you, if you're dealing with any other microcontroller, you might have to deal with this. So the other one is move LW. And frankly speaking, I spent so much time figuring this out because it drove me crazy, because the older assembly used to be upper, which kind of makes sense. Look up the upper byte, okay, the upper ones. Now the new assembler doesn't like this word upper. What it does, it actually uses low, high word. Okay, it's kind of crazy, but I found it. Okay, anyway, so now what this does, it'll take the upper, basically the last 8 bits in that 21, in the 21-bit, whatever it is. Like basically, it's gonna take the last high word, and it's just gonna put it in the working register. And now I can do the same thing, and I can say table pointer up F and A. Now my table pointer has a complete address. Now, if I do issue TBLRD, basically table read, and I have to put that asterisk, what would happen is it will take whatever value we have in the very first one, which is this value in here, which is the C9. It will take it and put it into that table latch, and then I can do whatever I want with it with that table latch. So my table latch would have it. I'm going to show you. We can move F from table latch to the working register, and now my working register have that value. So let's try that. Okay, we're gonna do this here. Okay, we're gonna pause it, reset. Okay, we're gonna do this. You see my program memory here has nothing in it. Okay, not program data memory has nothing in it. My program memory has the data that I have, which I defined. Okay, these are here, and this is where my program is. This isn't the right program, I think. It's okay, so it didn't assemble it yet. Okay, now it's right. Okay, so this is right. So we reset, we jump. Okay, so put my data here again, and this is basically this is what I have. So I'm putting the table pointer. So in order for me to figure out what the table pointer is, I need to go to the SFRs, but frankly speaking, I'm just going to go to the variables, and you can see I actually didn't add it in here. Let me just add it here. So we can just say table pointer, okay? And we can say table pointer high, low, and whatnot. It'll figure it out for me. Okay, so we're gonna do this and go through this, and you can see the table pointer is gonna start to change. You see the value in here? That's its address. This is the value. It started by putting EA. Well, what is it trying to do? It's actually trying to point to this particular location, which is here. You see it? It's actually EA. That's what it did. And now I'm gonna do the next stepping here. It's actually moving through it, and it's basically put 1FEA. This is exactly where it is. It's 1FEA. Okay, and it's gonna go to the upper one, which is 0. And now my table pointer is complete. Here, my table pointer is complete. It's pointing to this particular location in memory, which have these 2 bytes. Okay, actually, it's gonna just read that lower byte in here. That's if I do the table read, it's gonna just read that. So if I'm doing that, well, why don't I go to the special function register, and you can see them in here. Okay, so you can see the TBL, well, we're gonna have to scroll all the way to the T's. Okay, so here are the table pointers. So you can see them. The table pointer in here, the high has that, the low has this, and the upper has that 0. Okay, what do I care about? Well, I care about the tab latch, which is the table latch. So far, I have not implemented, or I have not executed the table read. And now once I do that execution, it will actually go to that location in memory, reads it, and place it into the table latch. And that's exactly what I saw. I wanted that C9. Now that C9 is actually in that special function register. I can do whatever I want with it. Now I moved it from the program memory to the table latch, and then in these instructions, what I did is I moved it to the working register, but I could have easily moved it just somewhere in here. Okay, which we're gonna see in a few seconds. So we're doing this, and you can see that my working register has that C9 in it, and now I can do whatever I want with it. This way I moved from program memory into the working register. So this just shows you what's happening. But more importantly, I wanted to see the table pointer did not move forward yet. It did not move forward. It's still moving. It's still pointing to the same thing. If I want to move to the next byte, remember this is 1FEA. If I want to move to the 35 in here, I'm gonna have to move to the B. Remember, these are jumping every 2 because I think they're instructions. This is not instructions, it's pointing to the C9. If I want to move to the 35, I need to actually, that pointer has to go to 1FEB. And the way I can do it is just by saying plus in here, and the plus would actually do the same, that exact thing for me. Okay, so we're gonna do that. We reset, we go to the jump, and then we're gonna put that in the table pointer, and you can see now I'm about to execute that table pointer. So again, the table pointer is, here's my SFR. The table pointer is here. It's pointing to the 1FEA. You're gonna see that once I execute this, it will put that C9 in my table latch, but it's also gonna move my pointer forward 1 location. So now it's pointing to the next one. So it's ready. Another TBLRD, I can actually read that and put it in the table latch and do whatever I want with it. Okay. All right, so why do we care about this? Okay, so now this is the mechanics of how to move from program memory all the way to data memory. But why do we care about it? Well, we care about it because of certain applications. Let me just show you some applications. So let me show you an application. So one application is, well, you might maybe you're interested in implementing some sort of a logic function. So this is a logic function. You've seen it in digital logic. You have a bunch of inputs. These are basically 4-bit inputs, and then you have an output. Let's call it A for now. Okay, and this is where the output, and you created a K-map, and you put a bunch of zeros and X's, and you reduced it, and you figured out what this A is. You don't have to do this if you can actually create it into memory. You can actually store this, and whenever you see a 0, it will output that, and so forth. And I'm going to show you this. So why do we care? Well, we can actually move more than one function. We can actually store up to 8 because we have a whole byte in here. So what I'm showing you here is actually 7 functions, and I can actually implement them just by storing these in that memory location. And because these are 7, I'm just going to add another bunch of zeros or ones in here. But let me explain to you what's happening in here. What you see in front of you is actually just the code for the 7th segment. So if I want to show the number, for example, 1, which is here, I just need to activate B and C. Well, B and C can be activated by 0 and 0. This is because I'm using a common anode. If you're using a common cathode, you're going to have to switch the zeros and ones. But the idea is, well, maybe what I have is I have a program that outputs that I just want to basically move from a certain number to some sort of a BCD. I want to generate that not BCD, the 7-segment pattern, so I can actually turn on or put a certain number in that BCD. Well, I can do it right here. This is one of the usages of actually storing data in program memory, because I'm going to store that particular table, and you're going to see it in a minute. I'm going to clean it up, I'm going to store it, and then I'm going to use it to figure out, well, if I want to display 5, what types of 1s and 0s I need to put, and I'm going to connect it to the proper pins in the 7-segment and display it. We're not going to do the connection today, but later on there will be a lab that will actually deal with this. But for today, I'm just showing you one way to do it. You don't need any decoders, you don't need anything. The microcontroller itself will output all of the 7-segment pins and all the signals necessary to do it. So what I'm going to do is I'm actually going to store, I don't care about these X's in here. These are basically when they're 10 and whatnot. I'm going to assume that we're not storing hex, just we're storing 0, 1, 2, 3, 4, 5, 6, 7, 8, all the way to 9. So I'm going to clean that table a little bit. By cleaning it, meaning I'm not going to store the last ones, and I'm going to put a bunch of ones in here because I need 8 bits. So if I'm doing this, I'm going to convert that to hex. This is the data that I want to save in my program memory. Okay, so I'm going to just take these and store them in my program memory. Okay, and from there, I'm going to write some sort of a functionality to do something very useful. So let me go ahead and just type these numbers in so that I don't waste your time in the video, and then we'll come back. Okay, so in here, you're going to see that I basically copied and pasted those codes that I've showed you on the slides. And these are the 7-segment patterns. This would be the 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These will show me the correct pattern on the 7 segment. So I saved them in program memory. And what I did here is I didn't change anything from the previous. What I'm doing is I'm loading the table pointer to point to that particular first byte in here, and now I'm ready to do whatever I want with it. So I can, and frankly speaking, the easiest thing to do is just to move it to data memory, all of it. So I'm going to take all these from program memory, save them in certain location in data memory, and from there I'm going to go and implement some sort of a functionality. Okay, so how do I move them into program memory? Well, again, I'm dealing with arrays. That means I need to do this indirect pointers with FSR0 or FSR1 or whatnot. So what I'm going to do is I'm going to say, okay, let's deal with the FSR. So I'm going to say load the FSR, and let's say 0 with some sort of a location, okay? And let's say, so that I don't want to remember what that location is, so I'm just going to put them right here. So I'm going to say, let's call it 7-segment here, okay? And that is equal to 0x. Let me store it at 41, for example. I'm going to store it starting from location 41. So it's going to be 41, 42, 43, 40. It doesn't matter where. Okay, and I'm going to say, okay, so the FSR0 is pointing to that particular location now. Good. So now what I need to do is I know that I have 10 bytes that I'm trying to read from program memory into data memory. So I will actually initiate some sort of a counter, and that's actually, I'm going to put it in the W and the working register. I'm going to put 10. And now I'm going to say, okay, let's move that 10 into some sort of a counter. Okay, let me just call that counter somewhere so that I don't have to remember it. Kind of like an index, kind of like what we did in the previous video. I will call that as an I, and I'm gonna say equals 0x70. Okay, so I'm gonna store that number in 70. So what I will be doing is I'm gonna move W to F, and what am I gonna move? I'm gonna move the content of the working register into I, so I'm gonna move 10 into the I. I'm gonna store it in the F. It has to change, the final answer have to be stored in the file register, and I'm using access RAM. Okay, so what I've done right now is now I'm pointing to the first location. It's not this one, but I'm pointing to that location, which is 81, and my FSR is pointing to location number 41, and I have the number 10 stored in I, so that I can actually iterate over 8 bytes. Okay, so all I have to do is just loop now. So I'm actually gonna tell you I'm gonna loop, and I'm gonna loop by, first I'm gonna read TBLRD, and I'm going to do store, and of course every single time I'm going to read a value, and then I'm going to move to the next value. I'm going to read the 81, and then I'm going to make the pointer move to the next one. That's what the plus is for. It's post increment. Okay, so it's going to post increment it. Now what am I going to do with the value? The value has been read to table latch, so I'm going to move it from table latch into, well, wherever the FSR 0 is pointing to, which technically INDF 0, but we're not going to use INDF 0 because I also want the FSR to move forward so that I can actually store the second byte. So what I'm going to do is I'm going to do, okay, let's do it with post increment 0. So now I know that I'm pointing, my table pointer is pointing to 81, my FSR 0 is pointing to that 41. So I'm gonna, this instruction will move 81 to the location 41, and then we'll move both pointers. The program pointer or the table pointer is going to move to point to the CF, and the FSR pointer is going to move from 41 to 42, so it's ready to do the same exact thing again. So all I have to do is just loop. But before I loop, I need to make sure that I'm dealing with my counter, so I'm going to decrement my F. I'm going to decrement I by 1. I'm going to do that, and now I'm going to say, well, as long as you're not 0, you will actually loop, and that will translate, will move all these values from the program memory into data memory. So this way I moved that, and it's ready so that I can do whatever I want with it. Okay, so let me just show you. We'll do that in here. Okay, I built it correctly. Okay, so we'll do that. We reset, we go to the beginning, which is reset vector, and then here, and you can see that all my data is stored in here. So I have 1, 2, 3, 4, 5 times 2, because each one of them is 2 bytes. It's 10 bytes, and that's exactly what I'm looking for. Okay, so you're gonna see that here, these instructions just basically are going through all the way. I'm just gonna stop wherever it says loop, okay, because all I'm doing is just moving data. So I'll do that, 1, 2, 3, 4, okay. And then here, okay, so now it's not yet at the table. Okay, so now it's a table read. So you can see now I am ready. I have the number 10 here. This is actually my I, and I have the data. It actually copied it for me. It shouldn't have. Okay, well, let me just do this. But you get the idea. I think I ran it. I forgot, like I ran it, like I didn't reset it correctly, but you get the idea. It actually, after, like if I go through this, you're going to see that it will be changing 81, CF, 92, and so forth. But it ran it because for some reason it ran, the simulator ran it. But anyway, bottom line is I moved that 81 all the way to 84, and you can see it from location 41 all the way to 4A. Okay, so I have all these values. These are the values, and I can do whatever I want with them. So what can I do with them? So let me show you the application. So this is a really useful application. So what we're going to be doing is we're going to write a program, and that program actually we're going to move the 7-segment pattern from the program memory to data memory. This is exactly what we've done a few seconds ago. And now I'm going to translate the content of WREG, which is the working register, from BCD to that is stored in the 4 least significant bit. Remember, BCD is 4 bits. Okay, so I'm just going to care for the 4 least significant bit in the working register, and I'm going to change it. So the working register will have some sort of a BCD, and I want you to write a program to change it into that 7-segment pattern. And I highly recommend that you pause the video and actually try to do it on your own before we find the solution. It's really not that difficult. You're going to have to deal with FSR 0 again and deal with it one more time. Okay. So let's go and try to solve it now. All right, so now we have everything in here. So I have that in table memory. You don't have to worry about moving that program memory. I already moved it for you. So what we need to do here is actually translate that. So let's assume that I'm going to move LW. So I'm going to move the number, let's say 4. Okay, this is 4 BCD. Okay, I'm gonna move the number 4. I'm gonna put it in the working register. The code I want to write right here is actually something that will just translate that 4 into the pattern that it should have been. So this is 0, 1, 2, and 3, and 4. So I want to see CC in the working register instead of 4. That's what I want to do. Okay, so what I'm going to do is I will utilize the FSR0 again. So what I'm going to do is I'm going to move the FSR0 to point to the first location of memory, which I know it's here. So I'm going to say, hey, load FSR0 into 7 segment. Okay, kind of like what we did at the very beginning in here. I'm just basically moving that pointer back to the beginning. And now what I'm going to do is there are certain instructions. I haven't showed you this, but I've showed you something very similar to the post increment 0, pre increment 0, post decrement 0, and whatnot. We have something else that is called plus W0. Let me show you. So what this instruction will tell me, okay, I'm going to move from the location in memory pointed to by FSR0. I can do that like this, but I don't want to. What I want is actually something pointed to by location number 4. So I need, this is, if I'm pointing here, I need to add 1, 2, 3, and 4. So I need to add 4 to it. I can of course loop till I get that 4, but there's actually a smarter way, and that smarter way is actually another special function register, another addressing way, an indirect addressing way, which is basically plus W0. What this does, it actually takes the value of the working register, would add it to whatever FSR0 is pointing to, and it will point to it. Okay, so my working register has 4. My FSR0 is pointing to that particular location here, which is 41. I'm going to take 4 and I'm going to add it to that pointer, which is FSR0. So I'm adding 41 to 4. So I'm adding 42, 43, 45, 40. Oh, well, 41 becomes 4, basically 1, 2, 3, and 4. So I'll be here at the 45 location. Okay, so I will be pointing to the correct pattern I'm interested in. And now what I'm doing is actually I'm moving that pattern into the working register, and that's it. So if I just run that program, you see it's a couple of lines. It's pretty, this actually plus W is pretty smart. It's actually what they call an offset. And it doesn't matter where your FSR is, as long as you know where you're beginning. For example, this is why I named it 7 segments. So I can actually completely change that and make it, for example, let's say 45. Okay, everything here will just change because my 45 would be the starting point. But just so that I don't confuse you, I'm just going to keep it at 41. Okay, and I'm going to run that program. And you're going to see that the end result is my working register should not have a 4, should have a CC in it. Okay, so we're going to reset. We're going to do, okay, run. Okay, and I'm going to do a run in here. And you can see that my working register has a CC in it. Okay, CC is actually the 7 segment pattern that will put, like if I take these 7 pins and connect them to 7 segment, I will see the number 4. Of course, I can change that any number. For example, let's assume that I want to do 7. Okay, which one is 7? Well, 0, 1, 2, 3, 4, 5, 6, and 7. So I should see 8F at the very end of here. Okay, so here's that. Okay, we run it. Okay, and then I'm going to pause it. And that's exactly what I got. The working register now has the letter 8F. Okay, so this is an application why we would need to store some data in memory. I did not have to code it in my code. What I did is I just basically worked it on paper, stored it in here, and just basically utilized it in a table. I moved it from program memory to data memory, and I utilized it. This might not be the best way to do it, but it's a way, and I've seen it, and I've used it in a different situation as well. All right.